So, good afternoon. For our fourth year design project, Yunjo and I are going to be talking to you about our reconfigurable microfluidic device, which is operating based on the principles of electrowetting. So, before we jump right into the design, first we're going to go into microfluidics is a broad topic. So, in our group, we decided to hone in on lab on a chip for two main reasons, being small sampling volume and high surface to volume ratio. So basically, stemming from that, we based our design criteria for the project on its customizability. We want the user to be able to approach it and customize it based on their microfluidic preferences and designs. We want to make this device portable. We're not trying to make a lab-sized desktop instrument. And also accessible. And by accessible, I mean we want to use materials and equipment that is commonplace, that doesn't require a high upfront investment. So now, going into our design a little bit more, our proposal is, for our device, we want our user to be able to approach a personal computer user interface and to be able to input their own desired channel configuration or droplet actuation pattern, and then have our device output their microfluidic design in a physical way. So to accomplish this output, for us meant that we looked into using electrowetting.
All right. And in the electrowetting phenomena, it involves a conducting liquid that when applied in the electric field through an applied voltage, it experiences a reduction in the surface tension between the substrate providing the charge and the liquid droplet. And when the applied voltage is there, the charges kind of cause a charge accumulation from the conducting liquid to flatten out, and it changes the contact angle. And this is kind of seen visually by the change in the contact angle theta of the water droplet on the substrate. Now, in the next slide, the more detailed illustration of that contact angle is given in relationship with the actuation voltage. Now, here in the graph kind of shows like an ideal water on a conducting substrate and shows how its contact angle just decreases with increasing voltage values. And the mechanism of this contact angle, as I said, is a result of these charge accumulations which create these electrostatic forces, right? And by the changing of this morphology, we can start to direct kind of like the motion of the water droplet based on the localized electric fields that are coming across from these electrodes. And this kind of is the main phenomena that we're exploiting to be able to create these digital microfluidic device.
So now what you're going to see here is a video of, this is a video of a 4x4 array of the electrodes using the electrowetting phenomenon. It's a little bit stuttery, but so what you're seeing above is a manual actuation of the phenomenon. So you see a black wire and a red wire. The black wire is our ground. The red wire is applying about 600 volts to charge the pad. So you see as the droplet reaches the new pad, the pad is applied, that the droplet is on, and then the potential is applied to the pad which we want the droplet to move towards. So now, just to go on a little bit about this configuration down here, the electrowetting configuration. Above our pads, you can see this is an LDPE film used as a dielectric layer, on top of which we coated it with a hydrophobic layer to help the droplet move around. And then this is a water droplet, deionized water, submerged in a silicon oil. And I mean, as much fun as it is to watch a droplet spin around in a circle on pads, we're not going to do this for 15 minutes. And our motivation, we envisioned this phenomenon, this movement, to lead to two main applications. The first application is for the creation of channels. So back to the electrode array. If we were to actuate, say, just a linear channel, then the droplet would spread across this entire channel, creating an entire channel of water. So being as the last slide, if it was immersed in a silicone oil, which was actually, it was a PDMS uncured, and then we were to add a curative to that, holding that and applying heat, we would result with a substrate with a customized channel embedded. An alternative application is we don't add a curative to the PDMS, and we have a droplet on the left and a droplet on the right. So within the droplet on the left, let's just say there's reactant A and reactant B. Maybe this is even a two-step reaction. And with our device, with our interface, we are able to control these individually and at the same time. So we can induce mixing, we can move them up, down, left, right, expose them to shearing elements. We can merge them whenever we want. We can bring the droplets together. And then when they're combined, we could then further split them and then perform analyses on them in parallel, or we could recombine them and just use the electrodes to bring our product to the desired location on the chip. It's a little animation to show you what I'm talking about. So all the while, this is just it's a way of just an additional applications. And from your product, you can expose it to different areas on the chip, be it a pH gradient or an additional electric field.
So while we have like these future perspectives about like what we want to do with our devices, it's time to like just kind of bring it into reality about how to construct such a device. And we look towards PBC to create like an efficient and cheap method of creating both our electrodes and the electronic logic of how to individually address these pads. It was like a cost-effective like method as opposed to microfabrication for just a rapid prototype for this project. And kind of to go in depth a bit into like what this circuit implies is that initially we just thought we could probably have a controller that would send the voltage to this electrode and then activate it to a high voltage. But the problem is that this actuation voltage requires like 100 to 1,000 volts, and that's not something like a controller would normally supply. So what we did was instead we decided to use a transistor, a BJT transistor, as an electronic switch to act as like a floodgate for high voltage, and then we would have the controllers control that transistor to rather to activate the pad with high voltage or keep it off. And another challenge that came across with trying to add to this design is that we needed a high voltage power supply. Initially, it was a bit hard to acquire, so we just decided to make our own. And for like a price range of around $30, we were able to get like a high voltage power supply that took in about 12 volts DC, and then we can get about to within the ranges of hundreds of volts, from 100 to 1,000 volts was what we needed for the actuation. And the attenuated power was around like 1 to 10 watts, right? And then over here is kind of like the summary of like the whole driving electronics of how these pads are actuated. We would have a personal computer that would take the input, as Alex mentioned, to create your configured channels. Then it will go into your microcontroller, which would tell which pixel or electrode pad to activate. The electronic switch then leads to the activation of the pad, which is actuated with the high voltage power supply. And this is kind of like the schematic of the high voltage power supply that we're using and the Arduino Uno microcontroller, right? So continuing from the hardware, we have to come from firmware that does like the heavy thinking of which pads to activate. And for this, we used an Arduino Uno microcontroller. And in here, the Arduino takes in serial communication, and through the serial communication interface, it takes in the firmware instructions and then outputs a digital signal that tells which channel or which pixel to activate. And while the firmware instructions, it can be a bit confusing to like write out and explain to the firmware, so we created this friendly user interface to be able to just kind of click which electrode that you want to activate to be able to actuate your water droplet. Simply, like with these squares, all you have to do is click one of the squares to activate it, indicated as red, and then your water droplet will be pulled towards that through the electrostatic force, and you can create some unique channel configurations. And so we can load up, like save and load up different types of channel formations, or we can even program like sequential electrodes to be activated one at a time to be able to kind of make some cool like patterns for the water droplet to be automated in its movement.
And now moving on from the hardware and the software, the next step in our design process was to optimize our electrowetting environment. Just a brief pause. Would you mind going and grabbing the PCB so that we could show it to them at the end of the presentation? Thank you. So what we're going to show here is the best. And by the best, our metric is the configuration with which we can actuate the water droplet using the lowest voltage at the pad. So we start at the bottom at the PCB level with a tin lead electrode, so 2 millimeters by 2 millimeters. Apply 2 or 3 drops of silicon oil, and then on top of this, we add a PVC spacer with a LDPE sort of in a basket formation, where the LDPE comes in as the dielectric sort of over top of the PVC spacer, and then we press that into the electrode to try and minimize the amount of space between the 2 layers. Next, we apply a hydrophobic coating. Actually, we apply it twice to the dielectric layer, and then on top of that is the silicone and water layer. So during the development process, we came to find that there were 3 really important attributes which were critical in the success of our configuration. The first was the dielectric strength. We experimented with a low dielectric strength, PTFE, and we found that the droplet became charged after not much time, and then the electrowetting phenomenon fell through and no longer operated. Another intimate contact between the dielectric and the pads was required. But for this, we used a silicone oil. We found this helped a lot because it helped us to push out any air from underneath the dielectric and anything else which might impede the electrical force from the droplet. And then third, a good hydrophobic coating to prevent the water droplet from getting caught on any elements while actuating. So moving on to our results and our observations from the project, the first and the most important was that we successfully obtained what we wanted. We had full control of the droplet. We could move it up, down, diagonally. We observed splitting, we observed merging of the droplet, any manipulations that we desired. And this picture on the right is a physical picture of what I was explaining before, where you can see the wrap and the PVC spacer. So it's important to note at this step that when I'm talking about wet and dry actuation, there's 2 methods we could do this. In wet, I'm referring to the DI water in a silicon oil, whereas dry, we found that without the silicon oil, with just the dielectric layer and a hydrophobic coating, we were also able to actuate the droplet. In the wet circumstances, we needed about 500 to 600 volts to properly actuate it, whereas under dry settings, we needed 900 or closer to 1,000. And as it mentions there, it really had a strong dependence on the hydrophobic. If the hydrophobic layer wasn't good, then it would get caught, and the dry actuation was not as simple. And then finally, tying back to our initial applications, the oil we used here was a PDMS uncured polymer. So we could, as per our initial application, have created a channel simply by adding a curative to the material. And we did do this experiment with adding water to PDMS and then allowing it to cure, and then the water maintains its shape and then falls out afterwards.
Yeah, go ahead. Oh wait, no, that's not real. All right, so that's the PCB board that we have been designing. So we'll be just passing that around to have a look at kind of like the heavy-duty transistors that went in there, and the demultiplexers, and things of that nature. So as we were packaging up our project, something that really came to our characteristic, like what we started to notice, was that we were able to really cut down on the costs of our device a lot lower than the cost projections that we have anticipated. And this is kind of like a diagram that kind of shows the partitions of like where our costs were distributed. And first of all, we were able to cut down the costs in the manufacturing by resorting to like PCBs as opposed to microfabrication. We also built our own high voltage power supply with a step-up transformer, which is shown by $30 in the gap over there. And also, we were able to get a fully functional device without really using those high capital materials like ITO-coated glass, which was really convenient for us. But what was actually a more interesting characteristic is that, I don't know if you noticed, but the kind of materials that we were using were all kind of commercially available like goods, like just plastic wrap, commercial hydrophobic coating. And this led us to like an inspiration for another projection, an avenue for our project, is that if we could do it, you probably can do it too. Like if you're a researcher or a microfluid enthusiast, if there are some, like you could go into, just have a grocery list of the kind of equipment you need. Just a PCB schematic is something that we could provide you, along with kind of like the instructions for the rest of the digital microfluidic device. So what we're essentially asking here is like, we can create like a virtual package that could potentially be set up in like an open source platform. It's something that could be accessible to everybody. So if you're a microfluidic enthusiast, this is something for you. And coming into the future works.
And as with any project of this scope, there are several areas which can still be improved. The first, as I was talking about earlier, the metric for our performance is the actuation value, or actuation voltage. So to improve that, on our PCB right now, the electrodes are indented above the board. So this leads to the water droplets preferentially sitting in between the electrodes, which is unideal. There's also a not insignificant gap in between the electrodes, which means that it requires more potential to pull it from electrode to electrode. And then again, hydrophobicity helps move the droplet from place to place. Second in this is to increase the complexity. We just demonstrated a 4x4 prototype. You could go, why not go to 8x8? If you added another plate on the top, you could introduce an input capillary and an output capillary, a syringe pump. You could control the flow in and out, add droplets whenever you want. There's lots of ways to add complexity to this and incorporate it into another form of research in this area. And this really leads to, going into this project, we didn't envision it as just making an electrofluidic or an electrowetting device, but we really wanted to start a digital microfluidics platform. Which digital microfluidics is the avenue through which we can create custom channels. You can create controllable droplet actuation paths, and further, where we see our platform as fitting is as a way of decreasing the barrier for users to get into digital microfluidics.
So we'd like to finally give an acknowledgement to our supervisor, Kellen Rand, for her laboratory for our wet chemical experiments, but most particularly John Saw, who's sitting right over there, for his help in setting up our, I guess, consulting us with their electronic components. And we couldn't have gotten that really nice video if not for him. And we didn't put it in the acknowledgement page, but that had to be said. So thank you. And so questions. You can come up. Come on, yeah, questions.
Okay, I'll take the plunge. Very nice, nice work, you guys. Not only did you seem to have a very well-rounded level of functionality, but this was an unusually good demonstration for something that typically doesn't work that well. So how well did it work? I mean, we saw a nice demo there, but did you have good days and bad days?
It was. Yeah, the last week was really stressful, just trying to get it together. But yeah, yeah. So I guess coming into the flaws of our experiment, right? We did show you the actuation that did work, but as you can see, even though we built like the software for the UI, we never showed you like a final product demonstration of the UI with the PCB, because essentially
I'm assuming the circuit
isn't quite there yet. Yeah.
I'm assuming also that you had some good days where the droplet would go everywhere you wanted to, and other days where it just sat there.
By the last days, that's kind of like the issue that we were seeing. But by the last days, I think we got a good control of it. Like we went through so many different types of dielectric layers, different methods. Like that configuration was like, I guess like maybe our 20th or 25th. Like we went through so many, but to a point, there are still like avenues that we want to keep going. It's improving for sure. And one of the ways is like, one of the things that we didn't mention, right, is that what would help with the experiment is if you had a conducting liquid, right, that reduces the actuation voltage. And there's definitely rooms for improvement where we can definitely get more like consistent results. But yeah, as you did mention that it was really bumpy until towards the end.
And to add to that, it's not the PCB in the end, the one that we showed passed around, it works, but the fundamental problem that we ran into was when we referred to as a high voltage power supply was actually just a step-up transformer. It took 10 volts and then bumped it up to 1,000, but we found that when it was connected with this PCB, this was some of the debugging that John Saad helped us out with, we found that the impedance on the transistor that we used here that would allow us to go up to 1K actually was too low. We were using the wrong type of transistor, so the final voltage at the pads was on the orders of 10 to 100 depending on our supply. We were getting a 1-to-1. We weren't getting the 10 to 1,000 that we were getting with the manual actuation. Right. So with a 1,000, with like a 1K power supply, we have hopes that this would still work.
Yeah. There's some interesting circuits inside those disposable cameras. I think those go to 600 volts, and some of my colleagues have similar circuits on CMOS. There's a nice demonstration, by the way, of a CMOS PCR unit with electrowetting input. But very nice. So, did you test it with other materials, other fluids?
We mostly, we tested it with the PDMS and deionized water. We were really focused on getting this, getting the PCB all
obviously working first.
And as mentioned that, we do have plans, like if we did have more time, we would definitely try more with conducting liquids. Obviously the ions would definitely help with the conduction, but if it's working for the water, we're assuming that it will work even better for solutions with higher ion concentrations.
It would be interesting to know now, can you make it work reliably without the ITO? Because I think almost everyone, possibly everyone, uses ITO on the top.
We didn't use any ITO.
Yeah, that video demonstration,
If you can make it work reliably, then I think that's a really nice step. And I'm assuming that you're writing at least one paper. Basically, you should.
We'll see.
Okay, very neat. Thank you.
So, what's an uncured polymer?
What I meant was non-cross-linked. It hasn't, the PDMS, it has a cross-linking agent that you add to it to provide the cross-links.
So it's not a PDMS anymore, it's poly. It's a polymer, right? It's a monomer, right? It's the precursor to the polymer. So you said it several times. Sorry. Not a huge issue given the amount of work you did. So, like I said, I'm a computational guy, so I don't. What kind of resolution do you think you can get down to? Because right now you haven't showed microfluidic. You've shown proof of concept for what we call macrofluidic.
Or millifluidic at this point, but yeah.
Actually, sorry. Professor Fedler, So I mean, but what kind of resolution do you think you can get down to with this type of system?
Using the standard PCB fabricators that we were using, 2 millimeters by 2 millimeters seemed like that was the norm for just a standard electrode like that.
Say you were like a startup with millions of dollars. What inherent limitations are there to your technology?
Well, it is a microfluidic device, so I don't really see the option to really look towards nanofluidics at this point. But for our case, I mean, like how we're packaging, like how we're excelling it, right, is that it is a digital microfluidic device that could be offered, for custom. How small they
She's asking about microfabrication.
So yes, it can go pretty small if you do microfabrication, but the issues of going too small is the spacing between the electrodes. Because if you turn on one electrode, it has a residual effect to the other electrode. So yeah, there is an effect if you go too small, but we never really tested for it.
I mean, look at the size of the transistors on this guy.
I understand. Okay, so then one might ask, when you were at the early design stage, what were the main benefits of this approach versus, say, additive manufacturing, 3D printing, for instance, or micro machining, there are many ways to do this.
It was just to incorporate both the circuitry and the electropads on one package.
In many ways, you could say that additive manufacturing is direct competition to this, in that it can create a custom design one-of prototyping type material.
So this is subtractive.
I guess so. Well, what we really wanted to, our initial insight into going into this project is that we wanted to create like a little package that will be able to allow for rapid prototyping of lab-on-a-chip devices. So this is a prototype device for a prototype device is what it is. Yeah.
Quick comment. 1 millimeter size squares is quite functional when it comes to things like PCR. I mean, that's a happy space to be in. So something like what you're presently envisaging could have quite a lot of applications. So.
All right. More to celebrate about.
Yeah.
Great.
Any questions from the audience? Thank you.
All right, thank you.
Thank you.